So on number 4, we have 4x squared y minus 3y equals x cubed. On the gateway test, now somebody in the other class said, how will I know, should I be looking for to know if I need to do implicit differentiation? X's and Y's kind of mixed in together. That's basically it. All the other problems will be y equals and then x's. That's all it'll be, y equals and then all x's. And that'll be 8 or 9 of the problems will be that. And 1 or 2 will look like this. So it'll be very easy to tell when do I need implicit differentiation, okay? Now, so we go ahead and do it. And what did we say was important about this one? Product rule. Now that one's a little easier to see. A lot of the problems, like number 9, they have something, something plus xy plus something, something. And for some reason on that xy, we forget the product rule. But we need it because it's x. It's one function of x times another function of x because y is a function of x. Okay? So we've got to do a product rule. All right, so on this one we do product rule. So I would stick the 4. You could leave the 4 out of all of it and distribute it, but that's kind of silly. Just put the 4 with the x squared and then treat the y as its own thing. So tell me the derivative using the product rule. 8x. Leave the y alone. I would not put a dot there. Nope. Plus 4x squared left alone. And the derivative of y is 1 y prime or just y prime. That is your product rule. Got to remember that. Minus the derivative of 3y. 3y prime equals derivative of this side. 3x squared. Squared. Okay, now, when you get to this point, and this would be what I would call an easy, just a basic implicit differentiation, which is probably what you're going to have on the gateway test. 21 and 22 are harder than that, and harder than you'll have to do on the gateway test because they just have a ton of algebra. The hard ones are going to be more of the quotient rule or some of those that get into multiple chain rules, stuff like that. The implicit differentiation one's not going to get all that messy. Okay? So, now what you have here is no different than if I gave you the problem 2x plus 3 equals 4x minus 7 and told you to solve that. You need to gather the x terms on one side and all the non-x terms to the other side, right? That's how you do it. So, that's what we're going to do. So all the y prime terms, because that's what I'm trying to find. So all the y prime terms are here. I'll just move the non-y prime terms over here. And I get this. And now do what? Take out a y prime. Gives me 4x squared minus 3. And then what? Divide by this, and I get 3x squared minus 8xy all over 4x squared minus 3. That is what you need to be able to do for the gateway test, right there. Now, part B said, you've got this problem, and you're supposed to write an explicit function of x, or of y. What does that mean? Get the y by itself. Now that's no different than what we were just talking about back here when we were saying get the y prime by itself. What you want to do is get the y terms together on one side, which they already are, get the non-y terms on the other side, and we can do what? We can factor out a y. So before we've done any derivative, we can just factor out a y. And then we can divide. And we got this. Now we haven't done a derivative yet. All we did was get the y by itself. But now I can do y prime by doing what? The quotient rule, right? Now this is just a basic quotient rule problem. So lead me through that. So what do I do? Derivative of the top. Bottom left alone. Top left alone. 3x all over all that squared. So, now, here on a quotient rule like this, I need to distribute. I do need to simplify this, right? So 3x, so that would be 12x to the fourth. I think they're not here. He was intent on getting that back. That was good. Did you catch him? Yeah. All right. Good job, man. All right. So, right, so we distribute 8x to the fourth here. We can combine some terms, so we get 4x to the fourth minus 9x squared all over. So this would be some simplifying I expect you to do. So in this problem, we got a little extra practice on at regular derivatives. That's fine. But now, listen. This should be the same as what we found in part A. They don't look quite the same. Why? This has got a y in it. This one doesn't. But we do know what y is. I mean, in this problem, we know y is that. If I took this y right here, if I took x cubed over 4x squared minus 3, plug that in right there for that y, and then did a bunch of algebra simplifying, we would find out that this one is actually the same as this one here. They actually are the same. Okay? Now, why couldn't you do that all the time? Well, because you can't always solve for y. If you look at number 19, or I think it's 19, I was thinking of. If you look at number 19, there's no way you could get the y terms all together and factor out a y, because one's a y cubed and one's a y. There's no way you could get the y by itself on that one like we did here. So there are times you have to do implicit differentiation. This happens to be one we can do either way. Okay? And so I'm just kind of pointing that out. Now, when you get to problem 19 and 20 and some of those, they add a little piece to it. They say, find the equation of the tangent line. Well, what do you need for the equation of the tangent line? Slope and 1 point. Well, they give you a point, right? They give you, on number 19, they give you the point 2, okay? So you're just going to put the 2 there and the 2 there. So what you need is a slope. How do you get that? You do y prime. So you go through on number 19 and you do the derivative, find y prime, plug in the point 2 for x and 2 for y, figure out what the slope is, and then just put it right there. So that's just a little extra step to do, but the basic part of the problem is find y prime, and you need implicit differentiation to do it. Okay? All right. So while we're on it, let's look at, say, 21 or 22. Well, I'm not going to take the time today to go through all of it because most of it's algebra, and you're not going to have that much algebra that you have to do on the gateway test. But on 21, it says what? 2
2x squared.
All that squared. I can hear you. 25xy. And then what's the point they give us? 1, 2. So there'd be a 1 there and a 2 there. So when I get done and I find y prime and I put in my point 1, 2, I'll get a slope and I'll stick it in there, and that'll be what they wanted in the problem. But the basic thing you need to be able to do here is the y prime. So we do this side, outside first, bring the 2 down in front, leave the inside alone to the first. No. Times, chain rule, we got to, because I've had people on Gateway do that. Every time they go to do the chain rule, when they go to times the derivative inside, they do a plus. It's time, don't confuse that with product rule. It's multiply by the derivative of the inside. So big parentheses, 2x plus 2y, y prime. And again, don't stick a dot in there or anything. It's just 2y, y prime. All right, equals. And then what about this side? That's a product rule, isn't it? So 25x derivative is 25, y left alone. 25x, y prime. Now, I'm just going to leave it at this point, but I'll just tell you what would have to happen next. I mean, if you got all of that, that's good. I mean, if you got all of that, you really have a good understanding of the y prime and the product rule, when to do it, and that stuff, and that's the key thing. Now, what's left here is to find y prime by itself. Now, that would be no different than if I gave you this problem here. X plus 2 times x minus 3, let me stick a 4 out in front of that, equals 2x minus 7. If I gave you that problem, what would you do first? You'd FOIL out, well, you might distribute the 4 into that first one maybe, or FOIL the parentheses and then distribute a 4 into them, right? Because what I want to do is gather all the x terms on one side and the non-x terms maybe on the other side, or maybe get 0 on one side since it's quadratic. Maybe that's what I'd want to do. But I'd want to FOIL this out so I could get a bunch of terms, so that maybe I can combine some like terms and I can move some stuff around. But first I have to FOIL and multiply this out. Well, that's what you have to do here. You just have to FOIL this out, because it's a binomial basically times a binomial. So you have to FOIL this out, distribute through the 4, and then you'll have like 4 terms on this side. A couple of them will have y prime in them. And then you'll have a couple terms over here. This one has a y prime in it. And you'll just gather the y prime terms to one side and the non-y prime terms to the other side. Factor out your y prime and away you go. So that's it. But it's just messy because there's just a lot of algebra with all the FOILing. Yes?
So if you're foiling and you take y squared times 2y prime,
Yeah.
so what would that be?
That'd be, if you took this, y squared times that would be 2 y cubed y prime. So right here, that times that would be 2y cubed y prime. And here you'd have 2x cubed, and the inners here, that'd be 2xy squared, and the outers here would be what? 2x squared y prime. Right. And so you would have, and then you'd stick 4 on all those, distribute the 4 to all those, and that's what you get. So it's kind of a mess, right? It's kind of a mess. If you've done 21, I wouldn't even bother with 22. I mean, you should do one of them, but 22 is very much the same. You probably got the idea. Okay? But that's it. I mean, that's implicit differentiation. And there's not a lot of extra practice in the book on those. They're pretty much those ones on that page. And so when you over the weekend or Monday, you may need to just go back and revisit some of those. Of course, you can make them up too. I mean, just make up problems with x's and y's kind of all mixed together in there. You can just make up functions and do it that way. Okay, not too hard to do there. And then just check them. But it's not easy. You'd have to check with somebody maybe. That's a downside. And you can't. I think there's a way to do them on the calculator. I haven't really even messed with it because we just don't ever do them on the calculator. So I just didn't bother to take the time to play with it. All right, so let's talk today about this. The last thing we have to do with, which is these trig rules in the derivative. So let's just put them up here. First of all, these are the 3. There's arc sine, arc cosine, arc tangent over here. Okay, and then I want to talk about those functions a little bit. Arc sine, arc cosine, arc tangent. Just remind you what that means. Okay, and show you where it comes from. But those 3 on the right. And this document is up on the website at the very bottom of our page, on our School Fusion page, in the Files section. It's called Derivative Rules. Okay? And so I've put that up there. So it's arc sine of u, just like the other ones we wrote, is 1 over the square root of 1 minus u squared, and then, of course, times u prime, whatever the inside. So as far as the gateway test and how it works, just like any other function. Just like any other function. The derivative of the outside, the arc sine is 1 over square root, 1 minus whatever's on the inside squared. And then you tack on the derivative of whatever's on the inside. Arc cosine's just like it, but it has a negative on top. Which kind of makes sense because we said all the cosines, cosine, cosecant, cotangent, all are negative. So arc cosine is also negative, so it kind of fits the pattern. And then arc tangent does not have a square root. That's not a typo. It does not have a square root, and it has a plus sign on the bottom. So I put stars by those, meaning you better look those over. You don't see them very often. There's not a lot of them to practice on the homework. So you just got to kind of make sure you look those over. All right. Now, if you don't have, I'm going to go away from this here for a minute, but if you don't have them, I'll put them back up here in a little bit. All right, I want to go over inverse functions real quick. And you would not have to write any of this down right at all, to be honest with you. Probably just if you'd follow along with it. Okay, I just want to remind you, first of all, inverse function, and this goes back to what Steve said earlier about inverses. We need to be kind of careful with the term inverse. Okay? Inverse functions mean, what's the first thing you think of besides this mirror image that I'm showing you on the screen? What's the first thing you think of when it comes to inverse functions? Besides the mirror image. Reflection, yeah, okay, you're not following what I'm thinking here. Okay, how about this? Because I'm sure you did, I'm pretty sure you did this last year, if not in Algebra 2, Advanced Math, one or the other. If I had y equals x squared, and I wanted to write the inverse of that function, you interchange or switch x and y. That's the one I want us to focus on. We interchange the x and the y. That's what an inverse function is. We switch the input and the output. Okay? And then we usually solve for y when we're doing that. And so we would get plus or minus square root of x. So x squared and square root of x are inverses. Now, what you get with x squared, of course, is a parabola that does this, and what you get with square root of x and plus or minus is the sideways one. Now, they are reflections. They are like mirror images. This one, of course, isn't even a function because we can't, fail the vertical line test. But interchange the x and the y. So now let's relate that to the trig functions. Okay? Oh, one other comment that's going to be important to us is this idea of slopes. Inverse functions have reciprocal slopes. Now earlier we were talking about opposite reciprocals. That's perpendicular. But just reciprocal slopes. Now, if you look at two pieces of a function that are mirror images there, it kind of makes sense because think about the rise and the run. The rise is the y and the run is the x. Well, what happens if you interchange the x and the y? The rise and the run are going to switch, right? They're going to flip. So it makes sense that inverse functions would have reciprocal slopes. Okay, but not only that, but look where the slopes happen. The slope on this one happens at an input of b. The slope on this one that's reciprocal happens at an input of a. Why? Because you switch the input and the output. Okay? So that means that x squared, we know x squared has slopes of 2x. So at 3, y prime of 3, you would get 6. Where would the inverse function, square root of x, have a slope of 1/6? Where would it have its reciprocal? Would it be at 3? Would it be at 9? Let's think about that a minute. If the point 39 is on this graph, then isn't its counterpart the point 93? So think about that a minute. This is x to the 1/2, so what's its derivative? 1/2 x to the negative 1/2, and now what if we did y prime at 9? That would be 1/2 times 9 to the negative 1/2. Now what's 9 to the negative 1/2? Well, it would be 1 over 9 to the 1/2. What's 9 to the 1/2? 3. 1 over 3 times 1 over 2 is 1/6. Does that make sense? So they have reciprocal slopes. Their mirror images have reciprocal slopes, but they're at two different input values. The first one's at 3, the other one is at 9, which was the output of the other one because we interchanged the input and the output. Okay? Now, that is something that we're going to need later on, that idea. That will show up again multiple times. Okay? And so that's an important concept as it comes to slope and derivatives. All right. So what about this thing about arc sine, arc cosine? How's that come? Well, here's a sine function. If we do its mirror image, that would be the one in blue. Okay? And if we do arc cosine, same thing. If we do arc tangent, same thing. Okay? So we get those mirror images. But how does this derivative come about? Well, I want to show you this right here. So I'm going to write this as sine. And again, you're not going to have to redo this, so don't even worry about following or writing this down. If sine and arc sine are inverse functions. Oh, and I want to say something about what Steve said about reciprocal when he used the word inverse. Here's where we screw up the word inverse. People say inverse, they think reciprocal all the time. Well, you're thinking of a special inverse. There's 3 different types of inverses that we could talk about. There's more, but these 3 for sure. There's an additive inverse, which is 5 and negative 5. Those are inverses. Those are additive inverses. What term do we usually use for 5 and negative 5? We always say opposite. But that's an additive inverse. There's multiplicative inverse, which is 5 and 1/5. That's what we always think of as reciprocal. Okay? And then there's function inverse, which is where you interchange the inputs and the outputs. Those are 3 different types of inverses. So when we just say inverse, without really being specific, it's kind of dangerous. Okay? So we're talking about function inverse. So sine and arc sine are inverses. So what should I get here? If I do sine of arc sine of x, I should just get x. It's like doing the square root of x squared. It's just x. They like undo each other. Okay? So square root of x squared, ln e to the x. What's ln e to the x? X. ln and e are inverses. Okay? ln e to the x is just x. Square root of x squared is just x. Sine of arc sine of x is just x. Okay, so this is a true statement right here. Let's do the derivative of both sides. Okay, here we go. So the derivative of this side, we do the derivative of the outside first, which is cosine. We leave the inside alone. Multiplied by the derivative of the inside, which would be the derivative of arc sine. Oh wait, we don't know what that is. Yeah, well we do. Let's pretend we don't know. So I'm just going to put question mark. No, I'm going to put arc sine prime. That's what I'm going to do. I'm going to put arc sine of x prime. I don't know what that is, which we're going to find out in a minute here. Okay? And that's got to equal, no? Well, yeah, but what is that? What's that expression? It's just 1, right? So I did the derivative of both sides. Now, what I'm trying to figure out is what is arc sine prime. I want to know what the derivative of arc sine is. So what can I do? Divide this over there. So arc sine of x prime is 1 over cosine of arc sine of x. Okay? Now, what's cosine of arc sine of x? Well, we got to go back to Mrs. Payne, or whoever your advanced math teacher was. Or geometry, this would be more, I'm not, yeah, Mrs. Clark's class would have done, all the advanced math classes would have done this. So, if I ask you, let's go back here. If I ask you for cosine of arc sine of 1/2, back in advanced math class, here's how you worked it. If you're not familiar or remembering this, here's how you worked it. Arc sine 1/2 is like saying, what angle has a sine of 1/2? What angle has a sine of 1/2? Pi over. Okay? Now remember, we said sine and arc sine are inverses. They're like interchanging their x and y. So when I say sine of pi 6 is 1/2, then that's the same as saying arc sine of 1/2 is pi 6, right? I just interchange their inputs and outputs. So arc sine of 1/2 is pi 6. Now you might have that memorized, but maybe you draw a picture of it. So you say, okay, where is the sine 1/2? Well, sine is the y, 1 is the hypotenuse, and so Pythagorean theorem would tell us that this is root 3 over 2. And we look at that triangle, and sure enough, that's the 30 right there. Whoops. So that's pi 6. Now, so that means the inside here is pi 6. So what's the cosine of that angle right there? It's root 3 over 2. It's the adjacent over the hypotenuse. It's root 3 over 2. That's how you work those problems. So back up here. Follow this now. Pay careful attention. Not that this ever matters, but pay attention anyway. No, but seriously, we're doing the same thing here. The difference is instead of saying arc sine of 1/2, we're saying arc sine of x. So what that is saying is that there's some angle whose sine is x. Now again, so let me draw it. Wouldn't that be the angle that had sine x? Whose sine was the answer x? It'd be opposite over hypotenuse, so x over 1. What would be this side right here? Pythagorean theorem. It'd be 1 squared minus x squared, and then the square root of that. So this would be square root. You can kind of see where this is headed. This is square root of 1 minus x squared. So that is what the inside is. This angle here, I don't just call it theta. This angle theta here is the angle whose sine is x. And now we want the cosine of that angle. What would be the cosine of this triangle here? It'd be this over 1. So the whole bottom is just square root 1 minus x squared. So the derivative of arc sine is that right there. So going back to, isn't that cool how that works out? I love it so much. I love it so much, Anna. All right. So that's where it comes from. We could do the same thing with arc sine, arc cosine, or arc tangent. Okay, we can get the same result. But that's where the rule comes from. All right. So very quickly here, and then let you work. No, we don't even have a stretch break because we only got like 2 minutes left. So here's the problem. So I got arc tangent of x squared plus e to the x, and I need to do the derivative. We'll do 2 of them. So y prime would be what? Hang on here a second. Oh wait, I'm not recording this, am I? I'm not right now. Jeez. No, I've been recording, but I didn't have it on the screen. Because I'm writing up there. Okay, arc tangent. So there's your rule right there, right?
Yes, sir.
All right. So those people watching at home, you'll just have to know. I did arc tangent of x squared plus e to the x. So the problem. Come on. All right. So y is arc tangent x squared plus e to the x. So that's like the u there. So y prime would be 1 over 1 plus
X plus x squared plus squared
all squared
times 2x plus
that easy. And then that could go up on top, but otherwise there's really nothing, you don't need to FOIL that out or anything. There's really nothing to be gained there. Most of the time there's nothing to be gained there. That would go on top and you would just do it. Okay? One other one. Y equals arc sine of x all cubed. So we're going to bring the 3 down in front. Wait. Nobody say anything. 3 arc sine of x, Brittany. I brought the 3 down in front.
Yeah, so it's a 2.
Wow, don't put me on class like that. That's
Because I knew you were going to get it this time.
Yeah, it was homework, guys.
I am for the next week. I'm picking on you. All right. 3 arc sine of x squared times. No, no. Times what?
1 over square root of 1 minus
X squared.
Right? So arcsine or arctangent could be the outer function, but it also could be the inside function too. All right, but so it just fits in with all the, and there's really nothing again we can do with that. So there's nothing much new there with the inverse straight derivative. You just memorize those rules, and then you treat them the same way you would with anything with outside inside changes. So the homework, I'm going to change the homework a little bit here. Well, yeah. Well, like I said the other day, depending on, it's shorter depending on how many times you want to take the gateway test. Okay? So,
7.
okay, there you go. Then it's definitely short. So 3, 4, where the line where it says 3, 4, that's this inverse trig stuff like 1 through 6 and 37 through 39. Those deal with more of the concepts of inverse function stuff. So we're going to throw those out right now.
Yeah.
Just worry about the gateway test.
Yeah.
Okay? So here is so basically your assignment is 190, 13 to 23 odd, which is like 5 problems. But, okay, that's the arc sine, arc cosine, because there's not very many. If you look at that section, there's like 10 problems that are arc sine, arc tangent. So maybe you save the even ones for later in the weekend or Monday or something if you want to practice a few more of these. Okay? But otherwise we got everything we need for the gateway test. So, the other part of the assignment is to go to that page 195. Some of you have been doing a great job. I mean, I've got people that are already done 20 problems off of page 195. Okay? Riley and some others. And so on page 195, do a whole bunch